Hello everyone, I'm Qianwen Xu, Assistant Professor in Electric Power Engineering at KTH and also PI for this project, Autonomous Coordination and Control of Smart Converters for Sustainable Power System. It's a great pleasure to present our project in this wonderful event, Digitalized in Stockholm. Our electric power system is changing to achieve the national target for 100% renewables. There are increasing integration of renewables into electric power system. Unfortunately, the intermittent renewables increase the risk of grid instability and cause the grid security issues. On the other hand, the renewable interface converters offer new promising methods to provide various functions for grid support. However, to efficiently and successfully utilize the grid support capabilities of converters require optimized coordination of a large number of converters, which is a significant challenge. First, converters have different functionalities for grid support, like voltage support, frequency support, inertial support. Then, how to decide when to operate at which function for so many converters to optimize the grid operation is challenging. Moreover, a large-scale power grids have hundreds of thousands of converters. Then, the computation and communication burden for coordination of so many converters are super large. Then how to develop a communication efficient solution is an urgent challenge to be addressed. So the aim of our project is to develop a smart autonomous power converters for optimal support of electric power system and to build a new control framework based on digitalization and AI that will enable smooth integration of renewable energy sources. To achieve these goals, we have developed a novel combined optimization and control algorithm for optimal coordination of multiple grid support functions and an AI-based scheme for autonomous control of smart converters with limited communication requirement. So our project is divided into two parts. The first part is the proposed combined optimization and control algorithm for coordination of multiple functional supports by smart converters. We propose this two-level framework for mode adaptation of smart converters. As mentioned, converters can operate in different modes to provide different grid support functions. So here we consider voltage regulation, line overload limitation, maintenance management, resilience enhancement, grid support functions. And we have this two-level framework to achieve this optimal coordination of multiple functions. The upper level strategy is to optimize this overall system that the operating mode of each inverter is determined hourly by solving the proposed mode adaptive optimization model. We have this 1 hour forecasts and corresponding simulation to construct the confidence set for estimating the probability of uncertainties. And then at a lower level, set points are determined every 15 minutes based on the solved modes. We formulate the two-stage robust stochastic model to solve this problem. The first stage is to select the modes of converter, and the second stage is to design the set points of the converter. This is the proposed flow chart to solve the proposed optimization model. So the first step, step 1 is to solve the optimal modes of each converter. Based on the hourly forecast simulation, we establish a two-stage model to decide the optimal modes of converters. And then we observe the uncertainties and solve the second stage model to decide the set points of converters. So the developed methods can fully utilization of capability of converters to provide different grid support functions. Here, then we conducted several case studies. We know here we consider converters with 4 grid support functions, including the maintenance management, line overload mitigation, resilience enhancement, and voltage regulation. These figures show the mode adaptive of converters with different modes, the set points of active power, reactive power, and the voltage profile under the proposed method. And we show different functions under the proposed method. For the maintenance management function, our proposed method can achieve significantly reduced load loss compared with conventional methods. And our proposed method to provide the voltage regulation support also shows that it can significantly reduce the load loss compared with the conventional methods. And also for the line overload mitigation support, the proposed method achieves this fully eliminated line overloads compared with the conventional methods. And the proposed method also achieves resilience enhancement support functions. We can see with the proposed method, the load loss is also significantly reduced under this mode. Next, we propose the AI-based scheme for autonomous control of smart converters. The previous work is a centralized optimization, and as we know, for large-scale grids, there are numerous converters. If centralized method due to the fast renewable energy fluctuation, the centralized controller need to do frequent calculation and communication with the local converters. That's high communication burden. Therefore, we propose the neural network-based decentralized control scheme. Here, we only focus on voltage support function that converters can provide reactive power to provide voltage regulation. Unlike centralized methods that we propose this neural network model to learn the relationship of reactive power injection of converters with their local voltage measurement. The procedure is like this. We have the historical renewable and load data, and we use centralized optimization results of the reactive power set point and the local voltage measurement as the input and output of this neural network. Then we train this neural network. The trained neural network will be deployed for each converter for the online implementation. So the converter equipped with this neural network controller can automatically provide optimal reactive power support given their local voltage measurement. Therefore, the proposed method achieves optimal reactive power support that is very approximate to centralized optimization, and we do not need real-time communication because for the real-time operation is totally decentralized, just need a local measurement of voltage. Then we perform a case study also in AIbased 33-bus system with the fluctuation of renewables and loads. We can see the voltage profile under the conventional centralized method without reactive power support and the conventional centralized optimization, as well as the proposed method. It shows that the voltage regulation of the capability of the proposed method is equivalent to centralized optimization method, that we can guarantee the voltage within the security range. And also we show this the power loss under the conventional droop control, which is a classical decentralized control method, as well as the centralized optimization method and the proposed method. So it shows that the power loss of the proposed method is equivalent to centralized optimization method and much smaller than the droop control method. And we also show the reactive power support profile to show that the proposed method is equivalent to centralized optimization method in reactive power support. So it shows the effectiveness of the proposed decentralized method in achieving the optimal voltage support. So in summary, our project provides the scientific foundations of grid support based on smart converters to construct tomorrow's smart power generation system, add significant value to digitalize the electric power industry, and enhance the resilience of electric power system with large-scale integration renewables for the sustainable and smart society. Thank you very much for your attention.